Hello everyone and welcome to this MASTS open forum session on anthropogenic energy in the marine environment. We've got three talks today. The first is myself talking about energy pollution by offshore wind farms. The second is by Momchil, who is talking about energy pollution by ships. And finally, the third, David's going to talk about how tidal stream turbines can change energy flow in shelf seas. Okay, I'm going to talk about how offshore wind farms can change mixing in shelf seas. This slide highlights the growth in offshore wind and that the UK growth is forecast to continue as both UK and Scottish governments have great aspirations. In general, wind turbines are getting larger and are starting to utilise a wide range of foundation systems other than the traditional monopiles. If you want to find out what the Scottish Government's energy supply aspirations are, a good place to look is the Draft Energy Strategy and Just Transition Plan. This figure shows how much capacity is in operation, under construction, and in the pipeline. For comparison, here are the same details for onshore wind, and you can see how whilst onshore wind is currently much greater than offshore wind, the aspiration is to grow offshore wind at a greater pace than onshore wind going forward. This slide illustrates the shelf sea setting in which this development is taking place. The world shelf seas cover only 7% of the ocean and only 0.5% of ocean volume, but 70% of tidal energy is dissipated in shelf seas, and it's estimated that 30% of productivity occurs in shelf seas. Shelf seas also punch above their weight in other ways, from fish landings to absorbing CO2 from the atmosphere. The nearshore regions are typically more tidally energetic, and the water column remains fully mixed all year. Deeper waters are less energetic, with weaker tides, and it's here, during the summer months, that the surface waters warm significantly more than the bottom water, and the water stratifies as there is insufficient vertical mixing and fronts appear. Here's a summary of the mechanisms of vertical mixing in shelf seas. The tide creates fast currents in shelf seas, and this causes friction both at the seabed and the surface, which creates vertical current shear. Turbulent eddies form and cascade to smaller scales, and there's heat dissipation and mixing occurring. So the production of turbulent kinetic energy is equal to the sum of the mixing plus turbulent kinetic energy dissipation. Here the thermocline acts as a barrier to mixing, and this is due to the strong density gradient within the thermocline. And most mixing occurs in the bottom and the surface mixed layers. Here I want to show you some model output from a region from the North Sea that undergoes seasonal stratification, where there happens to be a wind farm. This top figure here shows current speed as a function of time over about 3 months or so, March, April, May and June as well. You can clearly see the tidal fluctuations, so every day there's two tides, but you can also see the spring neaps tidal cycle. So roughly every 14 days you have a neap tide, and then a week later you have a spring tide, and so on. The next figure shows the potential energy anomaly, which is the amount of energy to completely remix the water column. So this is a good indication of how stratified the water is. So you can see early in the year the water is not stratified, and then you start to get these little peaks in PEA, which roughly coincide with just before the spring tide. So what's happening is the surface heating is sufficiently strong as you move into the spring months for stratification to occur, but then the spring tide comes along and the tidal velocity increases, and it's enough to remix the water column, so PEA reduces again. And in this example it actually occurs roughly about 3 times during March and April. When May comes along, the solar heating is sufficiently high that the increase in energy at spring tide is insufficient to completely remix the water column. And you can see PA plateauing slightly, but it doesn't reduce, and it continues to increase through the spring and the summer months. So come this June, you've got well established sustained stratification, which doesn't reduce at spring tide, and that will continue all summer. This last figure here shows sea surface chlorophyll from satellite observations, roughly in the same location. And you can see that in April, there were some peaks in chlorophyll at the surface. And this is the spring bloom that was almost certainly partly triggered by the increase in solar heating, but also the onset of stratification and the formations of fronts in this region as well. So here you have this ideal combination of solar heating from the surface and nutrient supply from the bottom, where you have which is being mixed up by reasonably strong tides during this intermittent phase of stratification. Come this sustained stratification, you can see that actually the nutrient supply at the surface is starting to dwindle, and the chlorophyll and therefore primary productivity starts to reduce in the surface waters. There's almost certainly still a subsurface chlorophyll maximum occurring, where you still have this sweet spot between solar heating and nutrient supply from the bottom, but this isn't visible in the satellite observations. Offshore wind development is now starting to occur in deeper waters on the continental shelf. Up to now, they've mainly been deployed in shallower waters, closer to the shore and in well-mixed areas. Deeper areas are likely to be seasonally stratified, and floating foundations are likely to be used. These figures are from a recent paper that suggests offshore wind infrastructure is likely to enhance mixing, such that in crucial areas, such as front and stratified regions, the timing, strength and extent of stratification could change. The effect would also likely depend on the type of foundations being used. This figure shows how our continental shelf can be divided up into different regimes in terms of their mixing. Here you can see close to the shore, typically you have permanently mixed areas, and in shallow waters you might get intermittently stratified regions. In deeper waters, which characterize much of the northern North Sea, for example, you can see that the sustained seasonal stratification occurs. This slide illustrates how structures in the marine environment can generate turbulence and mixing. So let's look at a cylinder in the first case. Here, flow around a cylinder, especially in unstratified flows, is generally well understood and well studied. In this example, vortices are shed off in the lee of the cylinder and coherent wakes form. These wakes are turbulent, and turbulence forms is very good at mixing vertically. So this is an example of how some anthropogenic turbulent kinetic energy can lead to mixing. But we're interested increasingly in stratified regimes. So this is much less well studied, but it's understood that many of the differences between stratified and unstratified flow are particularly important in the sort of turbulent regime, which we know form off the back of these structures. And increasingly, wind farm foundations are not going to be monopiles as we start developing in deeper waters. The idea of this slide is to illustrate how anthropogenic mixing by offshore wind farms might change a temperature profile through the water column. So here we have temperature high at the sea surface, lower at the bottom, with a thermocline in between. Typically in our shelf seas, you've got your tide and your wind imposing mixing both at the surface and the bottom. But if you add a wind farm, or in this case, a spar buoy in the surface, suddenly you've got some kind of anthropogenic mixing occurring throughout the surface mix layer and into the thermocline. So the resulting profile here is going to change slightly. You're going to have a reduced temperature at the surface and an increased temperature at the bottom as the heat from the surface is mixed downwards. This is a summary of the potential wind farm impacts on the ecosystem. So wind farms potentially could change mixing, and mixing controls stratification. Stratification occurs intermittently and seasonally. So the extent, location, and timing of stratification could change in a wind farm region. And this could lead to changes in nutrient pathways and in ecosystem function, which could ultimately lead to change in behaviours of fish, for example, and top predators. So in summary, shelf seas typically seasonally stratify, especially in deeper regions. And this leads to the spring phytoplankton bloom. Shelf seas punch above their weight in terms of productivity, and wind farms could potentially change the mixing. I think this is important because of the cumulative impact it might have as a result of many wind farms being built in shelf seas. And crucially, this could be both beneficial and detrimental in different areas in terms of productivity. We don't know yet whether it's going to increase or decrease it, and whether an increase or a decrease is bad. So this balance is unknown. Crucially, climate change is also going to be important and probably going to change stratification and primary productivity within our shelf seas. So wind farms could be used to mitigate climate change potentially in many unforeseen ways, perhaps. So there's potential links to net gain. Thank you.
Good morning, everyone. My name is Momchil Terziev. I'm a lecturer at the University of Strathclyde, and as Rory said and kindly introduced me, I'll be talking about anthropogenic energy in the marine environment by ships. If we think about a ship as a floating structure, as a moving floating structure, it actually interacts with the environment in a very large and very broad spectrum of ways. We have release from biofouling and antifouling coatings. We have release and frequent exchange of ballast water and transport of invasive species. Through that, we have black, gray waters. We have tank cleaning occasionally, cooling water and scrubbing water, and also some bilge water occasionally escaping. Of course, ships produce quite a bit of noise. I will show you some numbers on that later. Parts of the lubricants that isolate the shaft also escape into the environment. And in addition to that, sometimes ships will release solid waste. They will also produce chemical pollution through exhaust combustion particles that interact with the atmosphere and are deposited into the sea or the ocean as pollutants. Now, what I'm more interested in is the hydrodynamics, and this is what I will be talking to you about today. That includes, to some extent, the noise, but I'm more interested in let's say, the more physical disturbances that are essentially kinetic and potential energy. So, a bit of an introduction to what the hydrodynamics look like. And when a ship moves, it produces this very nice pattern of waves that we can split into divergent waves. These move at an angle of about 19.5 degrees relative to the ship track. And we also have the transverse waves that essentially follow the ship. They move in the ship direction. In addition, we have a turbulent wake that is produced by a combination of the action of the propeller and, of course, the hull itself. The majority of the flow is turbulent. But of course, this is highly idealized. This is a mathematical representation. I did not draw this myself of what the positions of the wave crests are. A much more realistic image of what ship waves look like is this image, which I produced using some computational fluid dynamics. And the components of the waves are less easily distinguished, but we still have very nicely the divergent waves, the transverse waves that follow the ship track, and the turbulent wake, which I have drawn myself in this image. Now, this kind of wave has been historically quite important, particularly in coastal and shallow areas, because they cause quite significant amounts of erosion. So the energy contained within these waves is maybe not so large compared to the overall kinetic energy in a given waterway, but these waves are very concentrated in time. So the turbulent wake is also quite interesting, and we study turbulent wakes in lots of different scenarios, from wind turbines, superstructures. You can even look at buildings and how air swirls around them. But I like this image because it shows the really nice resolution near the structure. But you can very clearly see how, as you move away from the structure, the quality of the solution, this is a computational fluid dynamics model, the quality of the solution decays. And this is done on purpose because we can't really maintain, or there's no point in maintaining that level of quality for long periods of time. And I'll tell you why this is important in a minute. But first, if you're anything like me, you travel on holiday for work, and one of the main things that you do is take photos of waves and boats. And I'll show you quite a few of these today. And what you can see is that this is a relatively small boat. The water depth it's not that restricted. But still, you can see that the turbulent wake and the area that is full of bubbles from the propeller is quite long, and you can also see the trajectory of the boat where we came from. Another interesting piece of physics that I really like is if I place my mouse here and leave it, you can see that the divergent wave is maintaining its position relative to the ship. So that pattern that I showed is if you're on the boat, it is stationary relative to you. I really like this video because it shows just how persistent the wake is. For a slow boat that doesn't have a big propeller, our wake is massive compared to the size of the boat. But these waves don't just stay as I showed you previously. And if you go out, you will see lots and lots of different types of waves. This is a very, very basic simulation of what happens as you continuously increase the speed. And what you see is that the transverse waves, the waves that are following the ship, essentially disappear. They are not able to keep up with the boat. And then the wave field narrows within an ever smaller cone behind the ship. This is, again, extremely basic, but in a more realistic simulation, you can see that we don't really have this kind of explosion that you saw previously. Now, this is important because it shows us two things. One is we can look at a boat and determine whether it is fast or slow by a single photo. If the waves are significant, if the cone is very narrow, we know that the boat is moving very fast. If the boats are very small, we can barely see them, then we know that the boat is moving relatively slow. And notice that as we accelerate past a given speed, the cone narrows and the boat essentially becomes like a bullet in terms of its weight. So here's another photo. This is a pusher barge, and what you see is a very wide and long. So this is about 100 meters long. This component here several times that length. So you can see a very large area of the water that is affected by passage of the vessel. Now, smooth water means upwelling. Essentially, mass of water is coming up from below and being pushed up against the water surface. And a very good analog for this is the opposite of a black hole. So if a black hole is a region of space where waves cannot escape, a white source, the opposite, is a region of space that waves cannot penetrate. And the reason why this region of space is smooth is because these little ripples are not able to penetrate it because of this upwelling. And this kind of upwelling obviously means mixing. And in this case, what you see is that this vessel is quite slow. There are barely any waves, even though we can see it, and we should be seeing very clearly the waves on the side. Nevertheless, because of its low speed, the energy that we give to the water to produce waves is basically insignificant. Even so, the wake is very massive, very strong, and very persistent. Another photo, this time a fast boat, and this is why I told you about the physics of how water waves are produced by boats and ships. This is a relatively small, I would say definitely less than 10 meters long vessel. and it came from this side of the image. Unfortunately, I didn't have the good sense of photographing it again closer when the boat reaches this side. But what you can see is that even when we have the very high speed regime, the bubbly wake, so the area of space where bubbles are still trapped in the water, which means that there is mixing and they cannot just escape up onto the water surface, is colossal in comparison to the size of the boat itself. So we could ask a question, for example, just how long are these waves? And this is an image from when I was flying into Edinburgh Airport. So this is the Firth Force, essentially. Based on what I can see in the image, when I really zoom in and what I saw on the day, this is some kind of general cargo ship of about probably 100 and something meters. So what I did is I did some image analysis and I created a box around the ship and copied it down to count how many times I can fit this vessel in the image. Now, if I really up the contrast and everything, I can see the wake going all the way here, but let's assume the wake stops there, in which case we have more than 20 times the ship length. And recall that for us to be able to see this, we either have that smooth region of space where there is upwelling or there are bubbles. And we can see that there is a white hue to this. So these are essentially, this is still a bubbly wake that is more than 20 times the ship length. Now, this is all very well and good, but you might ask me, what kind of data do you actually have? And luckily, some researchers did just that. They placed a sensor under the water and in a shipping lane and waited for ships to pass over so that they can detect the disturbance that is created. Now, in the top graph, we have noise levels. We have the position of the ship and an image of its bubbly wake. The extents of the graph start at just above 5 meters. That's on purpose so that they can avoid the vessel, which tells us that this is a relatively small vessel if it has a draft that is essentially less than 5 meters. Still, the vessel produces a very powerful and intense disturbance in terms of noise. You can see this is above 80 decibels, which is more than a food blender. And we know that that would be uncomfortable if you were subjected to that, which tells you that all of these marine animals, mammals, and other species can be quite strongly influenced by this level of noise, particularly in busy shipping lanes. In the bottom figure, we have essentially an estimate of the mixing or the turbulence in this caused by this boat passage. And what you can see is that although the vessel is relatively small, the mixing that it creates reaches all the way down to 30 meters, which is significant for oceanographic stratification, particularly if you're in coastal seas. Now, this is interesting, and obviously we have the problem of noise and disturbing the marine environment. We also have the mixing of the stratification, but these researchers found another effect, which I think is more important or more interesting, and it is essentially a spike in methane. What they did is they had sniffer drones. These are drones that detect what the plume or the exhaust plumes of the ships contain, which could be used, for example, for compliance with the law, so you can check whether someone is burning the fuel that they are really claiming that they are. What the researchers found is that after the plume has essentially dissipated or mostly dissipated from the exhaust of the ship, there is a spike in methane. And for context, methane is, I think, 28 times worse than carbon dioxide for global warming. And they estimate that this is due to nourishing of bacteria and microorganisms in the wake of the ship. So the stratification of the ocean and its mixing not only causes, or our mixing of the stratification of the ocean not only causes problems with large animals, we also know that there are increases in mortality of plankton and other species, We also produce methane, which is bad for climate change. And as far as I know, before these papers were published, this was not unknown, or we did not suspect that this was the case. So this presents a number of challenges that I can summarize as how do we predict these phenomena? Because if we can predict them, if we can model them or replicate them somehow accurately, then we can take steps, we can start to come up with strategies to mitigate them. Or at least we can include them in our overall understanding of the ocean and how ships interact with it better. Another really good question and research challenge is, what is the link between noise, turbulent wake length, and performance? Because if you're in a department like mine, we're only really up to now have been interested in the performance itself of the vessel and not so much about all the other stuff that the vessel creates. So I think realistically, the only way to do this would be through computational fluid dynamics, and this creates colossal problems because it's simply not possible to have good enough resolution of a turbulent wake over kilometers. And that's just not feasible, even with the most powerful supercomputing facilities. So we need to come up with ways that we can maintain that accuracy and robustness of the solution over extremely long distances. Thank you very much for your attention. I will now pass on to David.
Other than me. So this, not particularly old, but it is something that I started thinking about a decade ago, and I'm going to use a couple of things that I prepared a decade ago. One of which is a pictogram at the top, which if you want a translation of this is basically wall, rough sea bed, turbine, rough sea bed, islands, rough sea bed, wall going across. So the idea is we're going to look at how the roughness of the sea bed affects flows, both from a sort of an economic or engineering point of view and sort of an ecological point of view. And I'll start with just a little pretty picture, which is one of my favourite pictures ever, which I stole off the internet, which is of the block ships in Orkney. So I should explain I'm Heriot Watt academic based on the Orkney campus, and this is what one of the gaps on the North Sea side of Orkney looked like before they built the Churchill Barrier. So you've got these block ships, and you've got a very strong flow from right to left in this image, and you can see how the flow tries to find the gaps. Obviously the block ships are quite solid, but basically the same applies if you try and put a turbine in the water, but the flow will always try and find the gap. And if you just watch a river, you'll know this is true. If there's a boulder beneath the surface in a river, the flow tends to go around it and create all sorts of interesting hydraulic jumps and turbulence and so forth. So the same pretty much applies when we try and capture tidal energy from a channel. And what I'm going to talk about is, okay, how do you deal with the fact that the water wants to go round? So I'm going to start with this slide, which I will repeat at the right at the end. And some of this is sort of an assertion. I'm not going to get into the physics. The physics has been studied for about 20 years. So one of the things we know from a long time since is in principle, what you would do if you want to get as much energy out of a channel as possible is basically put something all the way across. So it's porous, but it is more or less spanning the entire width of a channel, or even the cross section of a channel. And that's efficient. But if you think about all the other reasons we might use a channel, we might use it for navigation. We might have environmental reasons to allow fish or sea mammals to migrate through it. It's probably never going to happen. You're never going to put a fence in. So you're going to end up leaving gaps. So what's the consequences of a gap? Well, first of all, the economic and engineering one is that you waste energy, because you end up with lots of strong flow going through somewhere you haven't put a tidal turbine, and less flow where tidal turbines are, as soon as you put the turbine in. It's also a fact that there's an environmental effect. So if you think about particularly for benthic environment, what defines the benthic environment? Well, one of the things is the flow speed. And so if you're suddenly allowing or you're inducing rapid flow at the bottom in the gaps, then you've altered the environment. And this can have a significant ecological detriment. So basically we say, well, gaps are bad. Don't want gaps, but you have to have gaps. So where do you go there? Where do you think, well, okay, I have to have a gap, but is there a way of reducing the amount of flow through that gap? And very simply, how you would reduce the flow through a gap is to add drag within that gap. And most plausibly, that drag would be basically adding to the bottom drag. So you would put something on the seabed that would add drag and at least reduce the increase in flow that you would get otherwise. And what we want to talk about is really just, can we find an acceptable way of doing that, and acceptable for a number of reasons. And that might be something that's considered natural in the inverted commas, what we might call a nature-based solution. So I'll come back to that slide at the end because it's sort of basically the whole talk. But I'll first of all talk a little bit about, okay, what do we do? We don't build fences. What we tend to do is build something like this. And I borrowed this slide from a former student, Mo, who basically designed a more realistic tidal array. So it's not a fence, but it's sort of groups of turbines. So you might have 3 turbines on the floating platform and set them together. And the idea here is the reason why you have them in this sort of staggered array is you allow the flow through the gap in the first row and then catch it in the second row and keep repeating that ad nauseam. In the bottom left, it's done schematically, and we've got 5 rows in all. In the top one, it's just with 2 rows. And you can see how the flow, which is the sort of orangey and red colors, tends to go through the gap in the front row, and then it does get at least partly effectively caught by the bottom row. So that's great if you could put an array across the whole width of the channel, but always there's going to be the outside. So we're still likely to have to leave a gap outside the array in total, and we should expect the flow to find its way around this thing. So it'd be all right if that's very shallow water, but if it's reasonably deep water, which we're likely to need to maintain for navigation, a lot of the flow is likely to end up going around the array. So what do we do about that? So first of all, I'll do a little bit of the simplest possible physical explanation of what happens here. Some of you may in long distance school physics classes been put together an electric circuit to make a light bulb switch on. So you may have done this. And so if you think about having a battery, and then we're going to have 2 regular resistances and 1 light bulb, which is basically another resistance, but it's the one we want, the thing we want to actually operate. If you go through the sums of this, and I'll leave it as homework, what you discover is if you have to have a bypass resistance, which we have as resistor 2 here, then that's going to steal current from a light bulb and stop the light bulb from lighting potentially. To stop that happening, it's always a good idea to increase the resistance of resistor 2, and that works even better if there's plenty of resistance in series. And so this is basically what we're doing with a little bit more complexity when we think about tidal flows in a channel, is we're, instead of trying to light a light bulb, we're trying to get as much flow through a turbine as possible. And in order to do that, we're going to try and fill any bypasses with a higher resistance, because that will help. Another slightly less simple representation of the same thing I've got here, which is what happens. It's a very simple representation. So A is a partial width array, and we put that in, and what happens is the flow immediately diverts around it, and you get, in this case, which is quite a common thing, is you would actually have a stronger flow not going through the array than you have through the array. Now, the thing about having two speeds of flow here, if you had two flows which had the same mean flow speed, they could merge happily, at least in principle, without creating any turbulence and without any waste of energy. But if they're going a different speed, and you think about this in terms of conservation of momentum and conservation of energy, is some of the kinetic energy in the mean flows has to be converted to turbulent energy, where we have C, in the process of those things merging. So not only have we got much stronger flow in the bypass than we had before we introduced the array, we also introduced a turbulence region, C. Neither of these things is necessarily a good thing. They're at least a change in the physical environments that can affect the ecological environment. So what can we do about that? Well, this is again a 10-year-old figure. This was basic idea was, okay, I've got 10 long green things are basically the size of a channel. Circular green things are islands. What you have if you just put an array in without doing any alteration is you have weak flow through the array and you have strong flow around it, which I've said is not a good thing. If you introduce roughness, you can, depending on how much you do, so this is a lot, you can reduce that bypass, and you might do this a little bit more conservatively, so you just end up with the same flow through all three if you did this slightly more conservatively. Now, the interesting thing about this, I think, from an environmental point of view, clearly economically, engineering wise, it's a good thing, but you can ask yourself, you know, which is imposing the greatest effect ecologically. Well, I think I would argue that though you'd have to have permission to add roughness, as we have on the right-hand side of this figure, if you don't, then you have altered the environment of those bypasses because you've increased the flow, which is about as invasive as you can get in terms of changing the environment. So is there an acceptable way of doing this? And that's sort of where we're going to try and look at. There's two obvious options, one of which is by altering the physical bed form. So this can be taking a plough to the seabed, potentially. I live in Orkney, and there's lots of bits of old concrete from 2 world wars hanging around Orkney. So you could have some very large blocks of concrete or large boulders introduced. And that's been looked at. 2 of the papers I got here are by Alice Lefebvre and collaborators, one of which is on the physics and one which is vegetated beds. And you can look at how essentially if you like, a seabed which has more roughness, perhaps dunes introduce kind of things. You can also think about what happens if you introduce boulders into a flow. It's again a bit like a river, and they will work. You will introduce seabed. The other thing you can do is have vegetated seabeds. I think this is a more interesting thing because it's probably quite difficult to take an old bit of World War II ephemera and throw it in the water. You might, however, wish to encourage the flora of the seabed because there's lots of other good reasons to do that other than my primary subject here. And that again has also been studied, and I'm not going to dwell on these. I'm just going to say these are things that have been looked at, and I think it's sort of an interesting idea. Can we make, particularly the latter one, can we make introducing cultivated vegetated beds in the right place something that's considered a good thing rather than a bad thing? So this is taken from a project that's happening locally. So I'm speaking from Orkney, and this is from about some of the kelp beds around one of the other islands of Orkney, around Sanday, and you get these big, quite well extensive kelp beds with a whole habitat biotype associated with those kelp beds, which are in place, considered a good thing. And the question is, can you make a case for introducing them where they don't already exist, but actually as part of an overall plan, they make good sense from all points of view. A few points about that. First of all, there are limits to when you can do this. So some kelp will grow pretty deep, but there is clearly a limitation. It requires light. It will take time to grow. And one thing about that is foresight is key, because if you think about what I said about, okay, we introduce turbines and then we say, oh, darn, there's too much flow going around. You've then got a very strong flow, and that's actually making it only more difficult to introduce something new. So you sort of have to do this bit first in the perfect world. So you slow down the flow where you're going to have bypasses, and then go forward. And this is all a little bit sort of counter, I suppose, how conservation preservation normally works. But I sort of put it out there as an idea that actually this might be the better solution than just leaving bypasses open. I'll just return finally to my last slide and then say this again. It really just summarizes the whole talk. And so just leave you at thought, well, maybe just leaving as you found it, if you like, a pristine environment in the gap near an array is not the best thing, but maybe you should actually just be prepared to be more active, proactive in altering that environment, and arguably for the greater good. So I'll just end there, and I think it's time for a Q&A, which Rory will chair, and it's for all three talks. So great to you, Rory.
That's brilliant. Thank you, David, and thank you, Mumchill. And I can open the floor to questions. Feel free to put your hand up or post your questions in the chat.